13. The Science of Sound. 13.1. Introduction. The human ear is a very important organ. Our ears provide us with information about the world around us. Even before birth, babies can hear the sounds of their environment. We learn to talk by listening to others. The delicate, sensitive hearing organ is easily damaged by injury, disease, or improper development. Perhaps you know someone who is deaf or hard of hearing. People who lose their hearing later in life often feel very isolated from those around them. They may use a variety of methods to communicate with each other and with the hearing world. Many use sign language, read lips, or even learn to speak without hearing their own voice. Some hearing people are surprised when deaf people react to a loud noise. How did they hear it? Could it be that sound can often be detected without hearing? Have you ever felt a sound? Maybe it was a low-flying jet over your home that caused the pictures on the wall to rattle. Or perhaps you have stroked a cat and felt its purr as it welcomed your attention. In this chapter, we examine the fascinating properties of sound, how it is produced, transmitted, and interpreted. 13.2 Sound waves. As a starting point, sound can be defined as the form of energy detectable by our ears. This definition is not entirely adequate because sound energy, or acoustic energy, does not have to be heard to be sound. Sound waves are carried through a medium. They can pass through gases, such as the atmosphere, liquids, such as oceans, and solids, such as metals, and the interior of the earth. Sound waves are more difficult to picture than water waves because they are longitudinal waves. In other words, the atoms and molecules of the medium oscillate back and forth, parallel to the direction of the wave motion. Sound waves are transmitted as periodic changes of particle density. A sound wave crest is a point of high particle density or a compression. As the crest passes, the natural repulsion of particles forces them apart. The trough of a sound wave is the point of lowest particle density, or a rarefaction. As the trough passes, normal random particle motion evens out their distribution, and then the next compression pushes them together again. Alternating compressions and rarefactions distinguish acoustic energy from other kinds of wave energy. How do you create a sound wave? To make a sound, something must vibrate in a medium. A tuning fork is one of the simplest ways to make sound. When a tuning fork is tapped, the tines or prongs of the fork vibrate, making a sound with a single frequency or pitch. If you look closely, you may be able to see the tines vibrate. These vibrations push on the air, first in one direction, then in the other, sending out waves of compressions and rarefactions. To see the periodic motion of these tines more clearly, immerse their tips into a tray full of water. The fork will cause ripples in the water, illustrating those it causes in the air. While we often use the word sound to refer to vibrations of matter that we can detect with our ears, we can also detect sound through our sense of touch. You have been able to feel as well as hear a cell phone when it vibrates. On a much larger scale, earthquakes are vibrations in the Earth's crust. During an earthquake, sometimes one can hear deep rumbling sounds. But as you well know, the destructiveness of earthquakes does not come from the sound they produce. It comes from the waves that shake the ground. You will learn more about these kinds of vibrations later in this chapter. 13.3. The Sound Medium. Robert Boyle conducted an experiment on sound in 1660. He suspended a watch with an alarm from a thread in the glass receiver of his famous vacuum pump. See Figure 13.6. He then pumped the air out of the vessel to form a vacuum. He and his assistants waited for the sounding of the watch's alarm. Time passed, and they did not hear it. Boyle had suspected that air was necessary to transmit sound. To confirm his hypothesis, Boyle opened a valve and allowed air to re-enter the chamber encasing the watch. As the air rushed in, the alarm grew louder and louder. Boyle had successfully demonstrated that sound needs a medium. Further experimentation showed that sound moves quite well through liquids and solids also. In fact, they generally are better acoustic media than air. 13.4. The speed of sound. How fast does sound travel? From 1708 to 1709, William Derham first accurately measured the speed of sound through air. He provided assistants with synchronized watches and pistols and stationed them at various distances, some several kilometers away. When they fired their guns at specified times, Derham recorded the time the sound was heard. Knowing their distances and the length of time between the scheduled firing and the sound of its boom, Derham calculated the speed of sound. He averaged the results of several trials and came up with a value that was surprisingly accurate. Scientists immediately tested Derham's value for the speed of sound. They fired guns and cannons of various sizes during the day and the night. They experimented at various altitudes and weather conditions to see what would affect the speed of sound. Their observations eventually indicated that the speed of sound is dependent on the density of air, but not on factors that do not affect the density of air, such as direction or time of day or year. Since Derham's time, scientists have measured the speed of sound with precise instruments. Today, the accepted speed of sound in air is 331.4 meters per second under standard atmospheric conditions, 0 degrees Celsius and 1 atmosphere. The speed of sound in air typically increases with temperature. At room temperature, the speed of sound is 345 meters per second, within 1% of the speed first determined by Derham. The speed at which sound travels through various media depends on the stiffness and temperature of the medium. In general, the stiffer the medium, the faster sound travels. Thus, sound generally travels fastest in solids, slower in liquids, and slowest in most gases. On the other hand, as density increases in a given material, the speed of sound decreases. Thus, the speed of sound in air is higher on a hot summer's day than on a cold winter's day. 13.5. Characteristics of sound waves. Chapter 12 discusses some basic properties of all waves: wavelength, frequency, amplitude, and interference. God created us with sensory organs that can receive different types of wave-like information from our environment and transmit this information to our brains. For each type of wave, the basic properties listed above are interpreted differently. Our eyes sense electromagnetic waves, and our brains interpret the frequency, amplitude, and interference of these waves as color, brightness, and pattern. Our ears sense sound waves. Pressure sensors in our skin can detect very low-frequency sounds as well. How do our ears and brains interpret the properties of sound waves? Musical instruments and other objects produce distinct sounds. The shape of the instrument, its materials, and the room or space in which the sound is produced all can affect the sound that reaches the ear. Our ears can detect several measurable properties of sound waves: pitch, high or low tones; intensity, soft or loud; quality, sounds like a violin or a steam whistle. All these factors affect every sound we hear. Pitch and frequency. Sound waves form a continuous acoustic spectrum of energy. This spectrum consists of waves with differing frequencies, or vibrations per second, including frequencies too low to hear, audible sounds, and frequencies too high to hear. Frequencies below human hearing are called infrasonic sounds, and those above are called ultrasonic sounds. Pitch is how high or how low an audible tone sounds to the human ear. The term refers to how we perceive a sound's frequency. The higher a sound's frequency, the higher its pitch. Chapter 12. That frequency is measured in hertz. The bottom note on an 88-key piano has a frequency of 27.5 hertz. The highest note has a frequency of about 4,186 hertz. Young children can hear pitches ranging from about 20 hertz to 20,000 hertz. As a person grows older, he typically loses the ability to hear higher frequencies. Do different pitches travel at different speeds through a uniform medium? What would it sound like if the lower notes from the choir traveled faster than the higher notes? You would hear them at different times, and the choir wouldn't sound unified. Since this doesn't happen, we can conclude that sounds of all pitches travel at the same speed. Experiments have confirmed this hypothesis. Loudness and intensity. Loudness is the response of your ear to the intensity of a sound wave. Intensity is a measure of the power contained in an acoustic wave. That is, the rate at which it transmits energy. The loudness of a sound depends on the sound's energy or power. Recall that the power of a mechanical wave is proportional to the square of its amplitude. Loudness also involves interpretation by the human brain. A sound of a certain intensity that seems painfully loud to one person may be just uncomfortably loud to another. Each person perceives sound intensity differently. The intensity of a sound wave is compared to the energy of a standard audible sound. The softest sound detectable by the average young person's ear is called the threshold of hearing, TOH. It corresponds to a specific sound pressure level, which is the maximum pressure exerted by a passing sound wave. This value is about 20 millionths of a newton per square meter, 20 micropascals. All other sound intensities are usually measured as a ratio compared to that sound amplitude. Because the range of audible sounds is so large, this ratio is expressed on a logarithmic scale as powers of 10. A logarithmic scale describes a wide range of values using a small range of numbers. Intensity is measured in units called decibels, dB, which were named for Alexander Graham Bell. The TOH has a loudness of about 0 decibels, near 1,000 hertz. A whisper is about 20 decibels and has 100 times as much energy as the TOH. Normal conversation is about 60 decibels, about 1,000,000 times the energy of the TOH. At 120 decibels, called the threshold of pain, sound becomes painfully loud and can permanently damage hearing. A 120 decibel noise has 1,000,000,000,000 times as much power as a sound at the threshold of hearing. Quality and harmonics. Tuning forks produce sound with mainly one frequency. When a musical instrument plays the same note, the sound is different from that of the tuning fork because a musical instrument plays mixtures of notes or acoustical tones. When a trumpeter, for example, plays a middle C, the instrument produces a mixture of frequencies that are multiples of middle C's frequency. This mixture of frequencies is the sound's quality. The particular sound of an instrument is its tone quality. Acoustic quality is what makes any sound unique. We make value judgments on whether sound is pleasant based on quality. Vibrating strings illustrate how instruments produce mixtures of notes. If you pluck a guitar string, for example, it vibrates as one big wave from end to end. See Figure 1311. The string produces the same tone each time it is plucked. This sound is called the fundamental tone, or simply the fundamental. It is a standing half wave, anchored at either end by 2 nodes. See Chapter 12 for definitions of these terms. If the string is tight enough, it also vibrates in other standing wave patterns at the same time, with more than one crest along the string. These shorter, faster vibrations produce higher pitches called overtones or harmonics. Harmonic frequencies are whole number multiples of the fundamental frequency. For example, if the fundamental frequency of 440 Hz is 1 times 440 Hz, then the first overtone of the 440 Hz tone is 2 times 440 Hz, or 880 Hz. When you pluck a guitar string, it typically produces several of these harmonics simultaneously. The fundamental tone is the loudest and determines the note people hear, but the quieter overtones give the guitar its unique quality. The construction and materials of an instrument determine its dominating harmonics, making each instrument sound distinct. 13.6 Sound Phenomena. The National Statuary Hall of the United States Capitol is sometimes called the Whispering Gallery. The building's architect unintentionally designed this elliptical room so that its hard plaster walls reflect sound from one end of the room to the other. Although no one in the center of the room would notice, a person at one end of the hall can easily hear the hushed conversation between persons at the other end. Why does this happen? Acoustics. A room or a building's acoustics is its effect on sound. Any type of enclosure will reflect sound. How well it does that is another matter. The science of acoustics is the study of controlling the sounds that reach our ears. Using this science, architects can build auditoriums with good acoustics so that the entire audience can hear adequately. They also try to minimize reverberations, multiple echoes of a sound formed when it reflects off distant surfaces. Reverberations may distract or irritate listeners because the same sounds, the original and the echo, arrive at slightly different times. Reverberations can make speech unintelligible and music jarring if the delays are more than a few milliseconds. In general, materials with hard surfaces are used where good sound reflection is desired. Chapter 12 discusses how reflection of a wave off a hard surface returns nearly all the wave's energy. Sometimes, hard surfaces are curved to reflect sound to specific areas to balance the overall sound. Often, the sides of a stage are angled to reflect sound outward to the audience. However, if sound is reflected back too strongly from different directions, reverberations may occur. They can be prevented by covering walls and ceilings with sound-absorbing materials. Soft, porous materials make good sound absorbers. Numerous small holes or openings greatly improve the sound muffling qualities of almost any material. Acoustic tiles are designed with such holes to trap sound energy. It's important to remember that sound is a form of energy. The greater the intensity, the farther sound waves travel. However, sound cannot travel forever because, like all energy, it changes to other forms when it interacts with matter. Though good acoustics are important, nothing compares to sheer volume for ensuring a performance is heard. Even the most acoustically advanced auditorium has some type of amplification system to increase the amplitude of sound waves, see section 13C. The excellent acoustics of some ancient amphitheaters, however, are nearly legendary. For example, the arena in Verona, Italy, is one of the largest Roman amphitheaters remaining in use today. Its acoustics are so good that 15,000 people can listen to an outdoor opera performance without artificial amplification. Resonance. Most objects have a frequency at which they naturally vibrate. If a sound matching an object's natural frequency is produced nearby, the object itself begins to vibrate. You may have noticed a car that rattles only at certain speeds, or a radio that buzzes only when playing certain sounds. These are examples of resonance. Acoustic resonance affects our daily lives. Resonance in your sinuses amplifies the sound of your voice. The air column in your ear canal amplifies incoming sounds so that you can clearly hear. The ornate wooden bodies of stringed instruments resonate to give these instruments their distinctive qualities. The air rushing at the proper angle over the opening of a bottle creates vibrations that resonate in the bottle. You may have heard the wind moaning as it blows through a building. These are resonant tones created as wind blows by gaps in windows or across chimney openings. The deep-toned blast of an ocean liner's horn depends on resonation in the horn. Organ pipes also resonate to produce loud, distinct tones with a small amount of air. The resonance of buildings is a major cause of building collapse in earthquake zones. As the ground shakes, the vibrations pass up into the building. If the frequency of the earthquake waves is similar to the building's natural frequency, the amplitude of the building's motion increases until the structure falls apart. Beats. When two waves with different frequencies interfere, they produce a new wave. The resulting waves, called beats, contain periodic crests and troughs that are much larger than either of the contributing waves. See Figure 12-33 on page 271. In sound waves, beats are heard when two sources are at slightly different frequencies. For example, when two musical instruments are not quite tuned together, you can hear a warbling or buzzing noise. To avoid this problem in a concert, the concertmaster plays a pure tone on his instrument, and the other musicians play the same note, listen for beats, and adjust their instruments to bring them into tune with the concertmaster's note. Digital devices used by musicians to tune instruments also employ the acoustic beat concept. The monitor is placed on or near the instrument, and a note is played. The monitor displays a series of lights or a digital scale, indicating the presence of a beat frequency, created by the interference between its internal tone and the instrument's note. The musical instrument is adjusted until the two sounds have exactly the same pitch, which is indicated by the beat displays disappearing or the illuminating of green lights on the device. The Doppler effect. In acoustics, the Doppler effect occurs when either the sound source or the listener moves relative to the other. The source's or listener's motion changes the rate at which the sound waves arrive at the listener, although the sound itself is being produced at a constant frequency. If the source is moving toward the listener, the sound waves are generated in the air closer together in the direction of motion, and the hearer receives more sound waves per second. The heard sound has a higher pitch than the source's. In the opposite case, sound waves are produced farther apart in the direction opposite that of the source's motion. If the source is moving away, the waves are farther apart as they arrive. Their pitch, as heard by the listener, is lower than the source's frequency. You have probably heard the Doppler effect in action. For example, the sirens of emergency vehicles change pitch as they whiz by you on the road. You can hear the same effect at auto raceways, at air shows, and near major highways. In each case, the droning of vehicle tires or the hum of engines changes pitch as cars and airplanes move relative to the listener. The Doppler effect on received sound depends on the speed of the sound's medium, as well as the relative motion of the source and the hearer. If the wind is blowing towards you from the direction of a stationary source of sound, the sound's frequency will be slightly higher than if the air is still. For example, a 20 km per hour, 12.4 miles per hour, wind will increase the pitch of a 1,500 Hz tone heard by a stationary listener about 24 Hz. This is why distant sounds like train horns or airplane engines seem to vary in pitch on gusty days.